Good evening. Welcome to the Lunar and Planetary Institute as we continue our 2013-2014 Cosmic Exploration Speaker Series. The universe is out to get us and what we can or can't do about it. Our first presentation a few months ago was about the sun and what it throws at us, which is bad usually. And tonight we're going to be talking about asteroid impacts on the Earth. And it's a little bit fortuitous. We actually were supposed to have this talk a few weeks ago, and we rescheduled it to this week, and it happened to coincide with a really cool event that Dr. Mackwell will tell you a little bit about here in a bit. Our next presentation will be March 6th, so we're taking a few months off, so don't forget March 6th. We have flyers out front for it. The topic will be on gamma ray bursts and supernova. And also note, our April presentation was originally the 17th. We have also rescheduled that for April 24th, so please note that. We have our email list, sign-up sheet out front as always. We also have some goodies on the table on the other side of the front door for you to pick up and take home. Teachers, if you're with us, we have your professional development certificates at the receptionist desk. Pick up one of those before you leave. And last time we asked you to fill out an evaluation. And so if you could do that again, even if you did do it a few months ago, we'll be walking around with an iPad again. If you want to do it that way, we have paper surveys at the front door, and we can also give you a slip with a URL you can take home and fill out if you want to when you get home. And don't forget our reception afterwards, of course. And we have a shuttle. I don't know if anybody here needed to take the shuttle tonight, but if you did, it will leave here for the last time and go back to the church at 9:30. So make sure you're on the 9:30 bus, so to speak, if you need to. All right. So to tell us more about tonight's speaker, I'm going to ask Dr. Stephen Mackwell to come up and do that. Dr. Mackwell is the director of the Lunar and Planetary Institute.
Thanks, Andy. Welcome. It's a great pleasure to have you here tonight. As Andy mentioned, we have an event going on in the building at the moment. It's a NASA-sponsored event that's here, was started up last night, it's going today, and then tomorrow morning. It's a continuation of a meeting that we started the 30th of September, an auspicious day. We started the meeting, it was supposed to go for 3 days. It lasted for one, then the government shut down. So 51 days later, we started it up again. As Andy mentioned, it's kind of something of a coincidence because the meeting is all about NASA's plans for an asteroid retrieval mission. And so it's rather interesting and coincidence in a way that we have David Kring scheduled to speak tonight on the recent Chelyabinsk airburst in Russia. So it's my great pleasure to introduce David Kring tonight. David is a senior staff scientist at the Lunar and Planetary Institute here. One of my scientists, it's a great pleasure to have him around. David did his bachelor's degree at Indiana University in geology, moved from there, did his PhD at Harvard University. From there, I should mention that while he was doing his undergraduate work, he was an intern here at the LPI in 1983. So he has a long history with the LPI. After he finished his PhD, he moved to the division of the Lunar and Planetary Laboratory at the University of Arizona and the Department of Geosciences at the University of Arizona, where he kind of moved up in the rungs to become an associate professor and managed the Space Imagery Center there. More recently, he moved here to the Lunar and Planetary Institute, first as a visiting scientist, and then decided he liked us so much he stayed and is now one of my senior scientists. David has a number of accomplishments. I could go through his long list of things that he's done and the commitments that he's made to the planetary science community over the years. But I'll just mention the awards that he's received. He's a Fellow of the Meteoritical Society, a Fellow of the Geological Society of America. He just recently received the Ron Greeley Award for Distinguished Services that is given out by the Geological Society of America. And he has an asteroid named after himself, which is quite fortuitous. David is an expert on impact processes, and much of the time he's been here, he's been the director of the Center for Lunar Science and Exploration here, running a group of people working on impact processes on the moon. But his background is much broader than that, and we're going to hear some of his breadth tonight when he's talking about asteroids. Of course, that's the other part of the impact process, not just what's hit, but what's hitting it. So, with no further ado, I will pass the microphone to David, who's going to talk about the 2013 Chelyabinsk airburst and the hazards of near-Earth asteroid impacts. David?
Okay. Thank you. Thank you very much. Let's go ahead and dig in. I want to start with the news of Friday, February 15th, 2013. For those of us in North America, you may have been waking up, turning on the radio, and getting the first burst of news. It may have been over lunch when colleagues around the coffee pot said, "Did you hear?" Or it may have been in the evening when you got home and you turned on the evening news. But the headline was, "Small asteroid penetrates Earth's atmosphere," or with some news organizations, a little bit more dramatic terminology. When this impact occurred, the sun was illuminating the eastern Pacific Ocean. Dawn was beginning to sweep westward across Asia as this asteroid made its way towards the Earth and impacted in the early morning hours coming from the direction of the sun. So it was completely unseen, unexpected, and as you will see in a few minutes, it startled a great number of people in Russia. Okay, to illustrate this trajectory towards the Earth, I'm going to use a video that some of my colleagues in the Czech Republic and the University of Western Ontario produced. So imagine yourself as a space cowboy sitting on top of this asteroid, and you're going to ride it all the way to the Earth. I am going to stop it, though, before you hit. They've asked me not to. So here we are approaching the Earth. We're 41 minutes out, so we're approaching the Earth very quick. We're now about 15 minutes out, screaming over Asia, just about to hit, and you can see the impact site just ahead of us on the limb of the Earth. Okay, it went screaming into the stratosphere, generating twin vortices tails behind the object as it was depositing a tremendous amount of kinetic energy in the atmosphere. And there was a series of high-energy detonations closer to the ground that generated shock waves, which really are the culprit behind the damage that so startled the people in Russia. The explosion shattered windows in the region, as you can see here, knocking them inward. Here we see smoke or dust rising where a factory wall collapsed inward and outward. Here is the aftermath of that collapsed wall from a similar perspective. And here's, you can see the debris of the wall that collapsed onto the sidewalk. Unfortunately, nobody was caught and buried beneath that debris. A lot of people were injured, but for the most part, thankfully, they were minor injuries. Now, I was showing you a perspective from the outside. I have to say, in these types of events, you are not assured safety on the interior. So I'm going to show you a couple of security films that captured. I have to defer to NASA TV. I was asked not to. Okay, yeah, I was asked not to. I'm sorry. So here is a video, and I'm going to start it, and you'll see a series of security videos that illustrate what people at work, just minding their own business, saw. Whoops, it didn't start quite right. Let me try that again. They quite clearly realized that there was something bad going on outside and cleared the room. Very smart of them. Okay, now we're going to see a warehouse. That's a shock wave and an air blast. Here's another office scene. And I like the fact that this gentleman went over to his colleague and picked her up and left. Very well done. Okay, so this obviously was a big event, but there's a couple of things I want to say about them. These stuff is falling onto the Earth all the time. And if we step outside on a clear night, you can oftentimes see meteors crossing the sky. These are little dust-sized particles. So the process of material hitting the Earth is not unique, it's not rare, it happens all the time. Fortunately, most of the debris hitting the Earth is small in size. This is a little diagram that illustrates the consequences of different types of material. Here are the meteors that you see burning up in the uppermost atmosphere when they are small dust-sized particles. Larger objects can penetrate deeper to the surface of the Earth. Sometimes they completely catastrophically fragment, so you cannot find any remnants of the object. But sometimes they'll reach the lower atmosphere, completely decelerate, and then fall to the Earth as a single meteorite. The bigger objects will generate lots of smoky trails. This is something akin to what Chelyabinsk did. Can have one or more multiple fragmentation or have fragmentation events and shower the ground with a series of objects. The largest or strongest objects can penetrate the entire atmosphere, hit the surface, and produce a hypervelocity impact crater. So message one is this is a common process. Message two is, thankfully, we are surrounded by an atmosphere. The atmosphere is a very important shield for those of us on Earth. As you may recall, for those of you who are a little bit older, when the astronauts were walking on the lunar surface, they were walking on a planetary surface without an atmosphere, and even these little micrometeoritic objects were plowing into the surface, creating micrometeoritic impact craters that were so energetic they were actually melting parts of the lunar surface continuously. Okay, so thankfully we have an atmosphere that protects us from objects like Chelyabinsk. Otherwise, it would have hit the ground and created some more damage. Okay, meteors are something that you can also see from space. I love this picture. This is captured by some of our colleagues across the street at the Johnson Space Center. When they were on orbit on the International Space Station, you can see this little Perseid meteor streaking into the upper atmosphere. And I would love to know if somebody saw this very same meteor on the ground. Don't know, but it would be fascinating for it to have been witnessed coming and going. Okay, not all fragmentation events also come with shock waves and damaging shock waves and air blasts. So this is an example. These are a few stones from the Portales Valley event of 1998. In this case, several dozen stones reached the surface of the Earth after witnesses reported hearing multiple detonations and seeing smoke trails. But in this case, the object was smaller. The detonations occurred a little bit higher, and there was no significant damage on the ground other than going through the wall of a barn and digging a few holes in the field and roads. Okay, so now let's drill in a little bit more about the Chelyabinsk properties itself. First of all, the diameter of the asteroid is about 20 meters, 66 feet for those of you who are used to English units. The asteroid hit the Earth with a velocity of about 19 kilometers per second. That's about 41,000 miles per hour. Most of the kinetic energy was deposited at an altitude of 35 to 25 kilometers above the surface, and the explosive energy of that event was approximately or equal to approximately 500 kilotons of TNT, which is a fairly substantial number. The energy of the bombs that destroyed Hiroshima and Nagasaki in World War II were about 15 kilotons. So this was a big event. Again, fortunately occurred at a fairly high altitude. This event is roughly an order of magnitude more energetic than the Sikhote-Alin event of 1947 that also occurred in Russia. It's roughly an order of magnitude less energetic than the Tunguska event of 1908, which occurred in Siberia. Russia obviously is a big continental mass and sees an unusually large amount of these events because of that surface area. Now I want to actually, it's important to say that the estimates of these past events, Sikhote-Alin and Tunguska, are our best guesses. Even Tunguska is a historical event, the records are quite clear on it, but there weren't arrays of devices out there to measure the event. It was in fact only investigated years later. And so when we try to evaluate the hazards of future impacts, it's important to understand that our database is really small. okay? And that really underscores the importance of the Chelyabinsk impact event. It was terrible that people were hurt, but for the first time we have a really good data point that relates the type of damage with the energy of the impact event. Okay, now, when this occurred on February 15th, there was, of course, a lot of discussion as to what hit, what entered the Earth's atmosphere. I've been telling you it's an asteroid, and of course we now know it's an asteroid, but what were the clues that led us to that conclusion? Some of these clues emerged really quickly. So what I'm showing here is the evidence from the impact velocity, and I am plotting on the y-axis the impact flux as a consequence of the impact velocity. Down here it's in terms of kilometers per second. Up here it's in terms of miles per second. Most of the impactors, and this is the follow the gold line, most of the impactors that hit the Earth are asteroids, and they have an average impact velocity of 18 kilometers per second. The Earth is also hit by some short period comets. They hit with velocities from about 30 to 35 kilometers per second. And then there's even a smaller number of long period comets that occasionally hit the Earth with velocities of 50 to about 55 kilometers per second on average. The Chelyabinsk object that hit the Earth on 15 February 2013 had an estimated velocity of 19 kilometers per second, which is this red line right here, which suggests that the object was in fact an asteroid. So that was our first clue. Now, there was a lot of video of this object crossing the sky, and scientists, in fact people in the public, together on lots of continents began piecing together the trajectory of that object through the sky, and then they worked that backward out into space and calculated a trajectory, or an orbit, excuse me, out in space. And I show that result here on this diagram. This is the Sun, the orbit of Mercury, the orbit of Venus, the orbit of Earth, orbit of Mars. And the particular orbit I'm showing you is the one that was determined by Paul Chodas at the Jet Propulsion Laboratory. And you can see that the orbit of Chelyabinsk before it hit the Earth emerged from the asteroid belt. Okay, so this is clue number 2, which is suggestive of an origin as an asteroid. Finally, not too long after the event occurred, people started reporting stones and pebbles and so on and so forth that had actually reached the surface and began collecting them. So let me show you actually an example of a Russian citizen. This is not a scientist, but simply a Russian citizen who's very curious about what has fallen in the woods by his home. And he's going to drill in. He's going to show you a little spot in the snow. There's that little hole, okay? Something's pierced the snow. He's going to excavate around that hole, and he's going to uncover what is buried beneath the surface. And scrape it away. Now, as it turns out, as these objects pierced the snow, they formed a tube, and that tube became icy, and they formed these little objects that the Russians call ice carrots. And at the bottom of the ice carrots, you see these little stones. Isn't that wonderful? Okay. So we have fragments of the object. So now we can take away all uncertainty. And in fact, analyses very quickly revealed that these are related to a type of meteorites that we call ordinary chondrites that we know for a lot of other reasons come from the asteroid belt. And I'll say something more about those meteorites in a few minutes. Now, as I said a few minutes ago, this was a 20-meter diameter object. It's fairly substantial, composed of ordinary chondrite material. Previously, the largest documented explosive fragmentation of an ordinary chondritic asteroid occurred in northwestern Arizona, seen here in this red circle, in an area called Gold Basin. That event involved an 8-meter diameter asteroid, so something substantially smaller, with a kinetic energy equivalent of 5 to 50 kilotons of TNT. So something that was significantly, by a factor of 10 to 100, smaller than the Chelyabinsk event. Nonetheless, it showered the surface with several thousand relics of the asteroid, which we collected over a period of years. And I want to point out that this is actually an event that occurred quite a long time ago. So we are extracting clues from the geologic record of these types of events over significant portions of geologic time. Now, Chelyabinsk was dramatic because it did get low enough in the atmosphere, it contained a lot of kinetic energy, and there was the explosion that generated the shock waves and air blasts. Now, it's important to understand that there are actually two sources of the shock waves and the air blasts. The first one has to do with the ballistic flight of that object through the atmosphere, and that's what this first bullet actually addresses. Shock waves are produced by objects moving faster than the speed of sound, i.e. Mach 1. Impacting near-Earth asteroids penetrate the atmosphere with a speed equal to or in excess of 11.2 kilometers per second. That's more than 25,000 miles per hour or greater than Mach 35, which produces a ballistic shock wave. The Chelyabinsk near-Earth asteroid was moving at Mach 60 to 61. Okay. Now, a second shock wave is produced by the catastrophic explosion. Okay? So that's just like a bomb going off anywhere that produces a radiating shock wave that can reach the surface of the Earth if it occurs above the surface of the Earth. And those shock waves are accompanied by high velocity air blasts or high velocity winds. Similar effects were measured around nuclear explosion test sites. This is an example of trees around a United States test during the Cold War. And you can see that the shock wave and the air blast actually is picking up a lot of dust, blowing it and blending over trees. Now the Tunguska impact event, which I've mentioned once and will refer to again, the event of 1908, was so energetic that when the shock wave and air blast encountered the forest in Siberia, it snapped those trees over like toothpicks over a region of about 2,000 square kilometers. Okay, now, this is a diagram that illustrates the consequence of the shock wave as it radiates from the point of origin. So this is increasing pressure over pressure and as a function of distance from that origin. And not surprisingly, the shock wave is more intense the closer you are to the impact. And as time progresses and the shock wave passes over a larger and larger area of the Earth, the energy or the magnitude of that shock wave decreases. Now, let's talk about what shock waves and air blasts have done at some other known geologic events. The best preserved, and I think the most dramatic near-Earth asteroid impact site is Beringer or Meteor Crater in northern Arizona. If you've not been there, you need to go there, okay? It's just down the road from the Grand Canyon. So when you go to the Grand Canyon, make a stop. This is the crater. It's 1.2 kilometers in diameter, okay? The guides there like to point out that if you had stood the Washington Monument on the floor of the crater, the tip of the monument would just reach the rim. This was a larger impact event. The object obviously reached the ground, but as I'll discuss a little bit later, the object wasn't that much bigger than the Chelyabinsk one. So that's actually important to keep in mind when you're trying to think about the hazards of these types of objects. Okay, so let's talk about what happened at Meteor Crater. This is a satellite view. It isn't actually. It's a space shuttle view. This is from Columbia. And here is the 1.2 kilometer crater right here in the center of the bullseye. Okay? Now, in small events like this one, it's hard to imagine this is a small event, but in the scheme of things it is, a fireball, shock wave, and air blast are the major environmental effects. This is not the size of the event that produces global climatic changes, mass extinctions, or anything of that sort. Nonetheless, the blast effect was immediately lethal for human-sized animals within the inner 6-kilometer diameter circle, that circle right there. Severe lung damage would occur within the next 10 to 12-kilometer diameter circle due to pressure pulse alone, and animals would be severely injured and unlikely to survive within that region. Now, winds would have exceeded 1,500 kilometers per hour within the inner circle and still exceed 100 kilometers per hour at radial distances of 25 kilometers, which is this third circle here. The outermost circle that I portrayed there at 50 kilometers represents the outer limit of severe to moderate damage to trees and any human structures of comparable strength to trees. And I say that because at the time of this impact event, 50,000 years ago, there weren't humans in the vicinity, and there certainly weren't any houses or anything of that sort. In contrast to what you'll sometimes hear visitors say on the rim of the crater. It's fascinating. Okay, now, this being 50,000 years ago, the landscape was different. In fact, the climate was different. We had cooler and wetter conditions. We were in the Ice Age. The animals that would have adorned the landscape are mammoths and mastodons, giant ground sloths, and bears, feeding and browsing and hunting. Okay? You'll see that red circle. That represents where the fireball would have scorched plants and animals up to a distance of 10 kilometers. The yellow zone represents where large animals were killed or wounded by pressure pulse and an air blast. I mean, for example, imagine the pressure pulse and air blast going over the landscape, picking up sticks and stones, and basically creating a fusillade or a shotgun blast that would have impaled animals living across the surface. So even animals that were wounded and not killed directly may have had a hard time surviving afterwards. Hurricane force winds would have then extended up to distances of 30 kilometers in all directions, which is represented by that blue circle. Okay. Now, as I said, that occurred 50,000 years ago. There were no humans in the region, but it's important to note that if such an event were to occur today, it has the capability of completely decimating a population of a modern city like Kansas City. So here is an outline of the metropolitan area of Kansas City. That is the circle represents the zone of severe to moderate damage. Anything in that zone would essentially be annihilated. Okay. Larger impact events affect larger regions. This is a picture of eastern Canada. In the center of the bullseye is a crater called Manickawagan. It's about 100 kilometers in diameter. And the white circle represents the region over which buildings and structures, if they were to occur there, would have been destroyed. So as you can see, it's a rather large area over a diameter of about 1,100 kilometers. Fortunately, and I've said this once before and I'll say it again, larger impact events occur far less frequently than small ones, which is good. And really good when you start to step up to Chicxulub-sized impact events, which are dinosaur-killing impact events, mass extinction-style impact events. And fortunately for us, these occur on average only once per 100 million years. Okay, in this case, a severe air blast represented by the red zone would have flattened any forest out to a distance of about 1,500 kilometers. Gale to hurricane force winds would have extended over the entire southern part of the North American continent as outlined by that yellow circle. In this case, these were actually minor consequences of the impact event. In this case, the impact event was so large it had global effects that extinguished most life on Earth at that time, 65 million years ago. Okay. So this is a little chart to kind of illustrate what I've just said in the last slides. The area affected by the blast increases as the impact energy increases. And so you see several things here plotted. There's Barringer Meteor Crater. There's the Reese Crater in Germany. There's Manickawagan, which I showed you in Canada. And here's the Chicxulub impact event in Mexico that affected the entire world. Chelyabinsk, you can see, is at the extreme small end of the types of events that produce air blast. Okay? So at some level, you look at this chart and you say, okay, they're not bad, inconsequential at some level. But it's important to also realize that as the world's population grows and occupies a larger fraction of Earth's surface, events like Chelyabinsk will potentially affect more people. So that is something I think to keep in mind. Okay. Now, you don't just have to look at the geologic past to see examples of these type of events. This is a modification of the diagram I showed you earlier. I've actually now put on here the trajectories of several relatively recent events. Here's Chelyabinsk itself coming in rather shallowly, detonating here with a blast of 500 kilotons. Just the year before, in 2012, the Sutter's Mill meteoroid detonated over California. How many people remember hearing about that? Okay. That had the energy of about 4 kilotons. And then in 2008, we had another asteroid come whizzing in. This one actually was detected before it hit, and so there were predictions as to where it would burst, and in fact, it did burst with a 1 kiloton blast over northern Sudan. Okay. So these events are something that occur on a relatively frequent time scale. Okay, now let's look at the asteroid itself. Okay, we have all these meteoritic fragments of it. Here is a picture just rotated of one of these fragments. It's a beautiful rock. You can see that it's a breccia. What do I mean by a breccia? It is a rock that is composed of broken fragments of older rocks. And they are cross-cut by these dark black veins. These veins are material of shock-melted portions of the asteroid that were created in an impact event on the asteroid long before it encountered the Earth. Okay? This brecciation process probably is responsible for reducing the structural integrity of the meteoroid and made it more susceptible for catastrophic fragmentation in the Earth's atmosphere. And this is something that's been argued on the basis of other meteoritic materials that have fallen to the Earth. Now, scientists love to take these paper-thin slices through rocks, and this is an example of that through the Chelyabinsk meteorite. And then we put it on a microscope, and this allows us to see the microscopic texture of the interior. And the meteoriticists in the audience are going to be drawn immediately to these circular objects that are scattered here and there throughout the object. These are chondrules. These represent molten droplets of rock, fiery rain that once existed in the solar nebula, this disk of dust and gas that used to circulate around the sun long before planets accreted. Okay? These chondrules eventually accreted to form small planetesimals, and those in turn eventually accreted to form the larger planets like Earth. That material, after it accreted into a small planetary body, was then affected by an impact event, and it created these dark black channels of impact melt that cross-cut the sample. Other parts of this meteoroid are completely black. Okay? None of those white fragments survive, and those black regions are visible in both the microscopic thin section and actually in whole specimens. This is a centimeter cubed. And this material has been severely shock damaged and melted by a pre-existing impact event on the asteroid before it actually encountered the Earth. Okay. Now, this is a picture to kind of illustrate the processes that this meteorite, or the parent body, suffered before it encountered the Earth. It came from the asteroid belt, and in the asteroid belt, the asteroids are bumping into each other. And any picture of the asteroid that you see returned by NASA spacecraft or other agency spacecraft, then you will inevitably see a surface that has been pockmarked or affected by collisional processes. Here, in fact, you can see an impact illustrated and going on. And I should say, I want to thank Dan Durda, who is actually the artist that reconstructed these. Some of these impact events are so catastrophic, the object might actually blow apart and reassemble, forming rubble piles. Now, this is a picture of the asteroid belt, okay? We have the Earth and the Moon. Here's Mars, here's Jupiter, and the asteroid belt is lying between Mars and Jupiter. Asteroids can survive for billions of years in the asteroid belt, up to 4.5 billion years. Every once in a while, those asteroids can migrate or will migrate into these channels. You can see there's these gulfs, these gaps. They're called Kirkwood gaps, where asteroids, when they reach those positions in the asteroid belt, are affected gravitationally by Jupiter, and the orbits are perturbed. So instead of having a nice circular orbit around the sun, they're perturbed into an elliptical orbit that crosses the orbits of the inner solar system planets like Mars, Earth, Venus, Mercury. And once they cross those orbits, they can collide with the planets. So that happened to Chelyabinsk at some point in time and put it on a collision course with Earth. Okay, now, we actually know quite a lot about the asteroids and near-Earth asteroids, to be more precise. We have 50,000 samples of near-Earth asteroids in our collections. Every meteorite's a near-Earth asteroid, okay? So we know something about those objects and how they were processed or evolved in the asteroid belt. We know something about how those objects evolve once they get into Earth-crossing orbits, and we know something about the collisional processes when they actually do encounter the Earth. Now, most of those samples, most of those 50,000 samples are what we call ordinary chondrites. That's the type of material Chelyabinsk is composed of, okay? Now, there's three types of ordinary chondrites. There is something called type H and I'm not going to worry too much about the distinctions between these. Just understand that there are some compositional differences that suggest they came from 3 different parent bodies, okay? So there's the type H ordinary chondrites, the type L ordinary chondrites, and the type LL ordinary chondrites. And our analyses and analyses by teams around the world have found that the Chelyabinsk object is derived from the LL parent body. We have almost 6,000 other samples from that parent body, so we can actually piece together a pretty good story about what that object experienced. And here, in fact, is one of those 6,000 samples. This is the Paragould meteorite, and I love this one because, first of all, it's a large mass. If you have gone to the Natural History Museum, the Smithsonian in Washington, D.C., and gone to the meteorite exhibit, you've seen it. You may not remember it, but you've seen it. And you can see here we have relic fragments of the asteroid that were caught up in an impact cratering event on its parent asteroid, and it, like Chelyabinsk, is cross-cut with these dark impact melted shock veins. So in many ways, Paragould has a lot of similarities to Chelyabinsk. Okay, because we have that collection of meteorites from the same parent body as Chelyabinsk, we can begin to piece together the collisional history of that parent body. And this is something that I've been doing with Tim Swindle at the University of Arizona and a student that Tim had. We've been analyzing every single impact melted ordinary chondrite or LL ordinary chondrite we can get our hands on. And what we have found is a large number of them were involved in impact cratering events 3.9 to 4.4 billion years ago. Okay? Then there's a large gap in our age distribution, which suggests there were few impacts on that parent body for a period of about 2 billion years. And then over the last 2 billion years, there have been scattered impact events affecting the surface of that object. One of those probably is responsible for jetazoning what became Chelyabinsk. Okay. Now, more recently, we can begin to analyze Chelyabinsk itself. Okay? And so here is some data that's just appeared in the literature. Our Russian colleagues have determined the age of that black shock-melted veins running through the sample were produced in an impact event 4.452 billion years ago, just before the pulse that Tim Swindle and I seen in other samples. One or more other less damaging impact events may have affected the object or the Chelyabinsk material more recently. And there was a final impact in space that occurred about 1.2 billion years ago that Kuni Nishizumi and colleagues at Berkeley detected. And this event exposed what became the surface of Chelyabinsk to space. So that is the event that liberated the object that we now know as Chelyabinsk. Okay, so let's now step through the history of this object. We begin nearly 4.56 billion years ago with the formation of molten droplet chondrules in the Solar Nebula. And all of that occurred within the first 4 million years of solar system history. Okay? Those chondrules and other dust particles accreted to form a parent body, the LL chondrite parent body, and that material was thermally metamorphosed over a period of about 10 million years. Now, based on the thermal metamorphic textures that we actually see in the Chelyabinsk meteorites, we can determine that the Chelyabinsk material used to be buried several kilometers beneath the surface. Okay. Large impact cratering event occurred on the surface about 115 million years ago, and we know that because of the analyses of the shock-blackened veins that cross-cut the sample. Analyses of other LL chondrites that are associated with Chelyabinsk indicated that that parent body was then hit severely by a large number of impact events between about 4.3 and 3.8 billion years ago. 1 or 2 impacts appear to have slightly affected the Chelyabinsk material during the last 500 million years. The meteoroid encountered a gravitational resonance with Jupiter. Its orbit was modified and it became a near-Earth asteroid at that point. And the surface of the Chelyabinsk meteoroid was exposed to cosmic radiation about 1.2 billion years ago, suggesting a collisional or fragmentation event. And then, of course, in 2013, earlier this year, it had its final collision with planet Earth. Okay, that's fascinating. Our colleagues in Japan have actually visited a fragment of the same LL chondrite parent body. It's called asteroid Itokawa. They sent the spacecraft Hayabusa out there. They explored the asteroid. They touched down. They collected a little bit of that material and they returned it to Earth. And so we can analyze it. We know it is composed of L-chondrite material. So here's the asteroid. For scale, it's 540 meters across. For comparison, there's the Orion crew vehicle that's going to carry astronauts beyond low Earth orbit, to the moon, asteroids, and potentially Mars. And here's the current International Space Station for scale as well. This is another view of the asteroid. It is a rocky body. Here, for scale, is a boulder on the surface of Itokawa that is 20 meters in size. That is the size of the Chelyabinsk meteoroid. And what's a little bit frightening about that is you suddenly realize there are a lot of potential Chelyabinsk boulders out there. Okay. Okay, so here's a little orbital diagram that indicates that Itokawa actually is part of the inner asteroid belt. Chelyabinsk is also part of the inner asteroid belt, although its orbit carried it a little bit farther into the asteroid belt. Now here's a comparison of scale. I want to begin with a picture of what the L-chondrite parent body looked like. It was roughly 100 kilometers in diameter. Okay? For comparison, there's asteroid Itokawa, and I've had to enlarge it by a factor of 8 simply so you could see it. Okay, Chelyabinsk you simply can't see at 20 meters. And this again drives home the point that I mentioned just a moment ago. This object has been fragmented, it's been scattered across space, producing a lot more Itokawas and Chelyabinsk, some of which could potentially hurt Earth in the future. Okay, now I want to say a couple of other things quickly. My minder's over there telling me you're starting to run out of time. But these are important things to understand if you're trying to understand the hazards of future impact events. The first thing I need to explain is, I made this point before, that the object that produced Beringer or a meteor crater in Arizona is very roughly the size of the Chelyabinsk object. Okay, now a lot of newspapers and pundits and whatnot said, oh, Chelyabinsk was half the size of some of these other events that were explosive. Okay, so let's actually explore what that means. Half the size or twice the size. So here's a picture, a stony asteroid 20 meters in diameter. Okay? Here is an object 2 times larger. Okay? 40 meters in diameter. Although it is 2 times larger in diameter, it has 8 times the volume and 8 times the mass if the density is the same. Okay? So is it 2 times or 8 times bigger? Okay, now let's put another twist on that. Those are stony asteroids. What happens if we're looking at an iron asteroid? An iron asteroid, also 2 times larger, has a higher density. It might have a density of 7 grams per cubic centimeter as opposed to 2 grams per cubic centimeter. So it is twice as large with 8 times the volume, but it has 28 times the mass. Okay? Now, kinetic energy, that is the explosive nature of these types of impact events, is 1/2 mv squared, 1/2 mass times velocity squared. Okay, so if Chelyabinsk is a 500 kiloton blast, an object with 28 times the mass has 28 times kinetic energy and would produce a 14 megaton blast. That's about what produced Meteor Crater in northern Arizona. So something 2 times larger can actually be quite a bit more destructive. Now, fearing the worst, our community and others at NASA and FEMA and the organizers of the Planetary Defense Conference says, what if something like this were to truly threaten the Earth in the future? So we ran an exercise earlier this year in April. David Morrison, I think, was there. It's a fascinating exercise. Everybody in the community was divided up into a series of teams, astronomers trying to detect the orbit and so on and so forth, trying to characterize an asteroid that might be threatening the Earth, a group that looked at mitigation techniques to try to get this thing away from the Earth before it hit. There was a team that tried to predict what the impact events would be. That was the team that I led. And you can see that there are several other governmental, press, space agency, and public teams that were put in a room and tried to work out how we would behave and what we would do if something was detected. Okay, so in this exercise, a threat was detected. There was a hypothetical asteroid, 2013 PDC-E, discovered on April 16, 2013. It appeared to be a threatening object, 200 to 300 meters in diameter. The initial probability of impact was 0.08% in 2028, that is about 15 years after discovery. If it were to impact, the velocity was estimated to be 12.4 kilometers per second with an energy equivalent of about 300 megatons of TNT. Note, if the object passed through what astronomers call a keyhole, the certainty of impact would have risen rather dramatically, and that event, if it were to occur, would occur in 2023. Okay, so in this simulation, we're trying to track the orbit, we're trying to better characterize the object, we're trying to predict what it happens, and as of 2019, the possible impact points, calculated impact points, lie along what's called a risk corridor, which you can see in a red line crossing across the globe. The possible impact sites include Southeast Asia, the coastal waters of China, Korea and Japan, Siberia, and the Arctic Ocean. As the orbit is better defined in 2019, the probability of impact has risen to 28%. Now that risk corridor goes around the world and passes directly over London and Paris, two rather populous points on the Earth, before passing over the Mediterranean Sea and northern Africa. Calculations of impact effect in all those different terrains had to be made to better inform emergency management in the countries along that corridor. Some people were panicking in the room, other people were taking advantage of the panic. Interesting. Okay, also as of 2019, several missions had been launched to deflect the asteroid and they had all failed. Tensions in the exercise started to go up. There was urgent discussions of nuclear weapons and last-ditch attempt to destroy the asteroid. Interestingly enough, some of the countries represented, in fact, some of the countries in the target zone did not want to use nuclear weapons because they were so philosophically opposed. The crisis grows in 2022. The probability of impact is now 100%. So the question is simply a matter of where it will occur. As the orbit is increasingly refined, the risk corridor shrinks to Europe and northern Africa. The impact will occur in the United Kingdom, France, the Mediterranean Sea, or northern Africa. And then these questions arise. Do you evacuate people? Are nuclear power stations shut down, et cetera, et cetera? Okay. Then impact occurred at 0700 on 21 November 2029. The impact fortunately occurred in the Mediterranean Sea. Nonetheless, shock waves roll over the surface of southern France. Tsunamis follow, crashing onto shorelines around the entire Mediterranean region, et cetera. There's, in general, tremendous devastation, and it is not a good day. We actually learned a lot in that exercise, and we all walked away with a lot of tasks to do, including those with NASA and FEMA. Okay, now, it's important to close by looking at, yes, I know, running out of time. Look at the probability of these impact events and how to prepare them. In a blue line here, what I'm plotting here, I actually should say Al Harris plotted, and is in an NRC document called Defending Planet Earth, is the impact interval of objects of different sizes. Okay? And as we've said before, smaller objects hit more frequently than bigger objects. This blue line represents the event that we just simulated, or I showed you in that simulation at the Planetary Defense Conference. This red line represents Chelyabinsk, and you see that a Chelyabinsk size event occurs on average once per 10 to 100 years. Okay? And I've said that several times, on average. Okay? That is the average cadence, but until we've detected all objects, any of these objects, including a mass extinction event, could occur tomorrow. Okay? So it's something important to keep in mind. Okay. So how do we move forward? To move forward, I want to actually draw your attention to this diagram, which is similar. You'll see that same curve. I've put the impact interval in years from this axis to this axis. And now over here are the number of objects explicitly indicated. And there's this red curve that Al Harris has put on this diagram. That is the curve illustrating what has been discovered, at least as of 2009. And you can see that there is a big gap. Okay? So what do we need to do to address future hazards? The first thing that I think we need to do is we need to have an environmental assessment of events that have occurred in the geologic past so that we have a foundation to estimate future events. Those events should include all cratering events and those air bursts that produce meteoritic and or geologic relics, like Meteor Crater impact event in northern Arizona, okay? Simultaneously, we need to have survey programs that are designed to identify potentially threatening objects. And here I'm pointing to this big detection gap. We don't have a very good understanding of the objects of that size domain. And here's a little factoid. Of the 20 million objects the size of Chelyabinsk, only 500 have been detected so far. Okay. Finally, mitigation concepts should be developed that can be implemented to reduce or completely resolve the hazard of near-Earth object any near-Earth object may pose for Earth. And it's important to understand that the earlier we detect an object that may hit the Earth, the easier it will be to prevent the impact event. Okay. Thank you. I'll take some questions now.
Here. We're going to let them ask too, and then if you folks want to, just come to one of those two microphones. You'll hear it in there.
Okay. So we're gonna, just real quick to Commissioner, we'll take two questions in here and then go to our overflow and see if they have any. And please wait till we bring the mic to you so we make sure it gets picked up on the cameras. Okay.
Just a simple question, the composition of the contract, any similarity to
Okay, so let me repeat the question. The question is, what can we say about the composition of the chondrite, or the impacting object, how does it compare to the Earth? Okay, to first order, chondritic meteorites, although they have subtle variations in chemistry, have the composition of the sun minus the gases, hydrogen and helium, okay? And to first order, all of the planets, Earth included, accreted from that same chondritic debris. So they have a lot of similarities. That is, Chelyabinsk has a lot of similarities to both the sun and to the Earth. Now, I don't want to imply with that very simple answer that the planets all have the same composition, and that's actually interesting. When we do compare the composition of the Earth, Mars, Venus, and so on, they should have started out accreting the same material and have the same composition. And when we find they don't, like Earth and Mars are a little bit distinct, that's a clue that something else interesting is going on. And that's what the planetary science community is spending a lot of time trying to understand.
Does anyone here have a question?
David, can you comment on the fact that the Chelyabinsk meteorite came in at a very shallow angle and could just as well have come in vertically over a city in terms of how the damage to a city would have been if it had come in straight down? Yeah,
I showed that plot of the Chelyabinsk trajectory and several other recent bolide events in the Earth's atmosphere, and you saw it had a relatively shallow angle. If the object had come in steeper, it would have deposited more of that energy at the Earth's surface based on computer simulations. Many of those are done by Mark Boslow in New Mexico at Los Alamos. And therefore, it could have been more destructive. Yeah, so the impact trajectory actually has a bearing on the consequences of the impact event.
Do we have any questions in the overflow room?
Not at this time.
Okay, we'll come back in here.
When you said 20 million Chelyabinsk-sized objects, is that among all asteroids or among near-Earth asteroids?
That's among all asteroids.
The early photos of the damage showed factory walls being knocked down. As a simple fix, could building codes be improved and help reduce the damage?
Yes, and I would say that buildings in earthquake zones would fare better from this type of impact event than in areas that don't have those enhanced construction techniques imposed on them. Yes.
How did you figure out the history of this thing by just looking at those grooves and things on there? That was amazing that you figured it out in much detail. How did you do that?
Well, that's what cosmochemists do. That's what the meteoritical community does. I mean, and I know that's kind of a glib answer, but literally, that's what we've been doing for over 100 years. We analyze the mineralogy and the chemistry of all of these objects, and that allows us to identify which meteorites can be grouped together, which meteorites came from the same parent body in the asteroid belt. And in fact, based on the collection of meteorites that we have, it appears that there were in excess of 100 small planets that survived between the orbits of Mars and Jupiter. And there's some ideas as to why they didn't accrete to Mars or some of the other planets. And in fact, it may have everything to do with the gravitational influence of Jupiter, which didn't allow that to occur. But it's based on the mineralogy and the chemistry of these objects. Now, the other part of the story that I told you had something to do with how deep it was buried. We can determine that because the deeper the object was buried, the hotter it got and the slower it cooled. So that can be equated to a depth. And then we outline some of the collisional history of the object. And we're able to determine that because if there is an impact event with sufficient energy, it will reset the radiometric clocks in the rock. And so we can determine the age of the new impact rock and then put that together in a collisional sequence.
Okay, go ahead.
We do have a question from the overflow room.
Yeah, I was interested in the basically the frequency that objects actually survive to impact the surface of the Earth. So, say in the last 100 years, what would be an average value for the number of impacts, and whether or not that's changed substantially over, the past that we know of.
Okay. Well, again, the smaller impacting objects occur far more frequently than the small one. And in fact, small meteorite-producing impact events are pretty darn common. I've done this calculation for Texas, and now that I live here, I should. But in Arizona, where I spent most of my life, the answer was 2 to 3 fist-sized meteorites fell in Arizona every year. Okay. Now, larger objects, the size of Chelyabinsk, they seem to be hitting the atmosphere somewhere between 10 and 100 years. And I have to say we can't be more precise for a couple of reasons. One, we don't have a lot of data. And two, that actually can vary quite a lot even if we did have a lot of data. In fact, I was discussing this very same issue with David Morrison, one of our country's most esteemed astronomers, just before the talk. Some of our colleagues will say it's a firm 20 to 30 years. Some of us think it's more like 50, 60, 70 years, but it could be a little bit longer. So there is some uncertainty to the answer that I can give you to that question. Now, the other part of that question is how often these things either cause damage or reach the ground. And there it's very important to understand that the size of the object and the strength of the object is very important when we're talking about these small objects, okay? When we talk about something that is mountainous in size, like the 10-kilometer object that produced the Chicxulub crater that wiped out dinosaurs, okay, that object was so big, it didn't see the atmosphere. It just went, okay? It's so massive, okay? But smaller objects that are both small and weak can catastrophically fragment. Stony asteroids are much weaker than iron asteroids, and so they tend to fragment in the atmosphere more often. And in fact, if you look at the Earth's smallest craters, they are almost exclusively produced by iron asteroids, and that is because the small iron asteroids can reach the surface while the smaller stony asteroids are unable to. And so they burst in the atmosphere.
Any more in the overflow?
Not at this time, thank you.
Okay, we'll take 2 more in here.
I heard that I don't know if it's the Air Force or the U.S. Military have been monitoring things coming through the atmosphere, and they have data that they were discussing releasing to astronomers to help provide more data. Do you know anything about that?
Yes. The U.S. government We refer to that as simply U.S. government sensors. We don't talk too much about the way in which they do this. I mean, obviously, those of us in the business understand that. But the U.S. government was very forthcoming. They turned over that data, and the estimate of 500 kilotons explosive energy is consistent with the U.S. government sensor data. Now, the energy can be estimated by several other techniques, one of which, interestingly enough, is a seismic technique that the world deployed as a countermeasure to nuclear weapons tests, okay? So this is deployed nationally so that if a country does detonate against treaties and agreements, a nuclear weapon, that will be detected. And so that system was also employed in determining or assessing the energy of the event.
Depends on who's close.
Most of the meteorites or asteroids that become meteorites impact the Earth. Your lecturer gave the asteroid belt as the main source of these meteorites that we have. Then I hear about meteorites from Mars that are found in Antarctica or of a different composition. How does Mars, when did those meteorites come from Mars, and how do we know the difference between those and the ones from the asteroid belt?
Yeah, that's a great question. Meteorites from Mars, and for that matter, meteorites from the moon, fascinate people in the meteoritic community because they are, in some sense, free sample return missions, okay? And what has happened in those cases is asteroids have hit the surface of Mars and hit the surface of the moon, and some of the material that's ejected in those events that in the crater forming process actually leave with velocities that allow them to escape those planetary gravities. Okay? Then they get into space, and some of that debris, it's a small proportion, but some of that debris will collide with the other planets like the Earth. And so we do have a wonderful collection of samples from Mars, and we have a wonderful collection of samples from the moon. Now, the meteorites that we understand today came from the moon were not actually discovered or recognized as being from the moon until about a decade after the Apollo program shut down. But we, in that case, had all of these wonderful samples that the astronauts had collected, brought back to Earth. We identified their very distinctive chemistry, and then when we saw a meteorite with the very same chemistry, we said, aha, we know where those come from. Now, the ones on Mars, that was a little trickier puzzle because, of course, we've not yet sent a crew, nor even a robotic sample return mission to Mars. But in that case, the atmosphere of Mars had been measured by landers, like Viking, okay? And then we got these samples back on Earth, and some very smart people, some of them right here at the Johnson Space Center, analyzed some shock-melted material within those meteorites and found that some of the atmosphere on their host planet was trapped. And the composition of that trapped gas turned out to be absolutely identical to what was being measured on the surface of Mars. So that has now been bolstered by a lot of other evidence, but we're really confident that we have a really handsome collection of samples from Mars. I have to say, as interesting as those are, those is a very tiny proportion of the meteorites that fall to Earth.
All right, well, let's take our speaker one more time. And if you have another question, see if you can catch them out in the lobby.
The closest restroom is through the door right there or right there. I have a survey online if anybody wants to fill it out. Enjoy your